Okay, so this is the first little video in chapter 19. So hopefully in class you talked a little bit, at least a couple minutes, about internal resistance of a battery and about EMF or electromotive force. So you should know that electromotive force isn't really a force, that's kind of a misnomer. Electromotive force is just kind of like um, it's the potential difference, so it's a voltage basically, but it's a very special voltage. It's the voltage before a circuit has been connected up. So when you think about an EMF, that's that symbol E right here, right? You want to think about an idealized kind of a voltage, kind of. All right. All right. So this problem that we've got has a little circuit diagram over here, and it looks like it has a 65 ohm resistor connected to the circuit. You've got a battery, you can tell there's the battery, and it also is in this problem showing an internal resistance on the battery. Let me point out that for the majority of circuit problems in this section, make sure you pay attention to the directions. There's only going to be a couple that actually ask you to consider internal resistance. The other ones are going to kind of ignore it, and you're just going to get practice with the other stuff. Okay, so make sure you only use the internal resistance little r on the problems it says. The problems that do have an internal resistance to the battery, they're going to be shown like this. So let's just consider like this whole part from A to B. This whole part of the circuit diagram represents the battery. Usually you just represent the battery as these little two unequal bars in a circuit diagram, but when you're considering internal resistance, you can see how you've got that little resistor. It's actually inside the battery, so you can see the terminals of the battery are being considered at A and at B, not at little bars like usual. So there won't be too many problems like this, but it's definitely something that comes up in real-world applications, so it might come up in one of our labs or something. Anyway, so this problem says in this little simple circuit that you have here, calculate the current, and let's just do it one step at a time. So we have the terminal voltage is the electromotive force, that voltage, minus the current through the circuit that's running through it times the internal resistance, right? And it looks like we do have the internal resistance. They said this battery has a half ohm internal resistance, so usually it should be pretty small. I guess it could be big in some situations though. Okay, so what are we trying to solve for here? We're trying to solve for current, right? It said find the current first. So we can solve for I. So we should say, how can we solve for I? That shouldn't be a big deal. But let's think about what the voltage is going to be first. So isn't that voltage between A and B also equal to the current times the resistance? And while we're on this topic, let's point out that this big R is being considered as this resistor up here. When you're doing circuit diagrams, it's not completely true, but you know in physics we make lots of assumptions to make the problems easier when you start out. There is some resistance in these wires hooking up to that resistor too, right? But if you listen to the little lecture I gave about circuit symbols, anytime you have a straight line like that, you're considering the resistance in that wire to be negligible. In other words, it's so small we're not even going to consider it. So in other words, Ohm's law for this circuit, we're just going to think about big R for that resistor. Okay. Anyway, so that's going to be equal to this script E symbol. I'm going to write it like this because I'm just terrible at writing script E's. And minus IR. So remember they wanted us to solve for current, so we should probably do that. So we should get I's on the same side, right? So plus, I'm going to add that one to the other side. I don't know what they're going to do, but okay. And then I can factor out I. So I have just the current, so it's the big resistance plus that little internal resistance from the battery. And then we've got the idealized electromotive force over there. So in other words, the current is going to be that electromotive force from the source, from the battery, divided by the sum of the two resistances. So the idealized voltage of this battery was 12, right? So we're going to go 12 divided by 65 plus a half ohm. Get a bigger equals going on there. And we get about 0.183. It's current, so amps. Oh my gosh, that's the worst amps ever, but that's what we've got. Okay, part B says calculate the terminal voltage V sub A, AB, the voltage between these two terminals in this actual circuit. So it's a very practical thing. So what is the actual voltage between those two things? So that's going to be this electromotive force, which we said for this battery, if there's nothing connected, it's 12, minus the amps in the circuit. We just calculated that, right? So 0.183 times the internal resistance of 0.5. So this is going to show us V sub AB is not the idealized voltage, but it's like the actual voltage in the circuit, right? E is representing the idealized voltage. So that's kind of the difference here. Don't let it freak you out. Anyway, so it's going to be somewhat less, I would think. That's kind of what happens. You get a little bit less. This is why car headlights flicker when you turn them on. Anyway, so you do this calculation and you get 11.9 volts. So you can see the voltage drop in this situation is not that much. So voltage drop, we've talked about it a couple times now. I think now it should be clear what voltage drop is. Voltage drop is due to the internal resistance of a power source, so the internal resistance of a battery or some kind of AC motor. Even those have an internal resistance. It's usually small, but you do get a small voltage drop because of it if you're looking for exact figures or precise figures. Okay. So we've got that. Did it ask anything else? Oh yeah, the power dissipated by both resistors. So the power dissipated by a resistor, let's see, isn't power, one way to express it is I squared times resistance. Let's use that one, I think. So we're going to go 0.183 because that's the amperage in our battery, the current. And we'll square that and take it times the big resistor of 65 ohms. So that's how much power that resistor is dissipating. That's how much energy it's using per unit time, right? That's what power is. So 2.18 watts per unit time. So it's using 2.18 joules per second. That's what the big resistor is using. Obviously, the smaller resistor should be using something smaller. So I squared little r. So the battery, just in and of itself, being connected up, it uses some power. So if you connected a battery just to wires, it would be using some power, not just because of the wires, but also because of the battery's internal resistance. And that just has to do with how a battery is chemically constructed. So we're not going to get into it beyond that. 0.5 there. Gotta love my fives. And that's 0.02 watts. So not a lot of power being consumed by that internal resistor, but some. Okay, see you next time.